Uranus is the seventh planet of the solar system, the third in diameter and the fourth in mass. It was discovered in 1781 by the English astronomer William Herschel and was named after the Greek sky god Uranus. Uranus is the most mysterious and least studied planet of the solar system. When in 1986 the space station Voyager 2 transmitted images of this ice giant to Earth, scientists described the blue planet as inexpressive, since it does not have bright bands like Jupiter, nor does it have prominent rings like Saturn. And in terms of temperature indicators, Uranus is even colder than Neptune, which is farther from the Sun. However, despite this ordinary appearance, Uranus has unique characteristics. A remarkable magnetosphere, an unusual axial inclination, which differs from the rest of the planets of the solar system, and a particular chemical composition. Dear traveler, good morning. Today we are going to explore the limits of the solar system to discover the mysterious ice giant Uranus. Before leaving for a new, exciting adventure, think about liking the video and subscribing to the channel to not miss anything. Thank you, and have a nice trip! Uranus is the third largest planet of the solar system. With 25,362 kilometers, or 15,700 miles, the radius of Uranus is slightly larger than that of Neptune. It is also the seventh planet from the Sun. Beyond it, there is only Neptune, if we do not take into account the dwarf planet Pluto. The mass of the planet has been determined by calculations based on astronomical observations of the gravitational influence that Uranus exerts on its moons. Although the volume of Uranus is 63 times larger than that of our Earth, its mass is only 14.5 times larger than the Earth, which makes it the least massive of the giant planets of the solar system. This is due to the fact that the average density of Uranus is 1.27 grams per cubic centimeter, a little more than that of water. Thus, it is the second least dense planet in the solar system, after Saturn. These low densities are typical of the four giant planets, which are composed mainly of light chemical elements. The planet Uranus is located at a little more than 19 astronomical units from the Sun, i.e. 19 times farther than the Earth from the Sun, i.e. about 2.9 billion kilometers, so its orbital motion is hardly perceptible and requires long-term observations. Following an elongated orbit, Uranus can reach a maximum distance, called aphelion, of about 20 astronomical units, and a minimum distance, called a perihelion, of 18 astronomical units from the star. By the way, Uranus has the biggest difference between aphelion and perihelion than any other planet of the solar system. Since the planets of the solar system are constantly in motion, the distance between them changes daily. Thus, at its closest, Uranus is 2.7 billion kilometers from Earth, or more than 1.8 billion miles. The greatest distance between the planets is 3.2 billion kilometers, or almost 3 billion miles. For a long time, it was impossible to determine the rotation period of Uranus around its axis from observations made from Earth. It was only when the Voyager 2 probe flew close to Uranus that it turned out that the rotation of the latter around its axis takes 17 hours and 14 minutes. But gas giants do not rotate like rocky planets. The speeds differ according to the latitudes. Since in the upper layers of the atmosphere, the winds blow at a speed of up to 240 meters per second in the direction of rotation of the planet, the clouds there can make a complete revolution around the planet in only 14 hours. As the rotation axis of Uranus is almost in the plane of its orbit, it moves around the Sun in a rolling motion. This characteristic is unique in our solar system. All the other planets turn around our star like a top. This is one of the most remarkable phenomena of Uranus, which remains unexplained. For most planets, including the Earth, the rotation axis is almost vertical, i.e. perpendicular to the plane of the planet's orbit. Rotating around the vertical axis, they also move in a circle, in their orbit around the Sun. This type of rotation creates a daily change of day and night over almost the entire surface of the planet, except in the polar regions, where, because of the tilt of the planet's axis, the change of light and dark periods occurs less frequently. The polar day and polar night last, for example, at the Earth's poles almost 6 months. On Uranus, things are different. Its axis of rotation is not perpendicular, but almost parallel to the plane of the orbit, with an inclination between them of 98 degrees, which leads to a number of unusual phenomena which do not occur on any other planet. One of them, extremely strange, is the change of the seasons. In fact, Uranus makes one revolution around the Sun in 84 Earth years. In other words, since the discovery of Uranus by William Herschel in 1781, this planet has only completed its third revolution. For us, this is a long period, more than 2 centuries, but for Uranus, it is only the 3rd year since its discovery. During this time, the 4 seasons, spring, summer, autumn, and winter, alternate, with a duration of almost 21 Earth years for each one. During the summer season in the northern hemisphere of Uranus, a day lasts continuously, more than 20 Earth years. During all this time, the southern hemisphere is plunged in total darkness, where winter reigns, which can also be called polar night. During the spring and autumn periods, daily sunrises and sunsets occur on Uranus. Further along the orbit, as the planet moves towards the zone corresponding to winter in the northern hemisphere, extreme lighting conditions are reproduced. As a result, the southern hemisphere becomes constantly illuminated, and the northern hemisphere plunges into the darkness of the polar night for more than 20 Earth years. At the poles and at the equator of Uranus, the change of seasons occurs in a completely different way. At the equator, the year of Uranus includes 2 summers and 2 winters, and the duration of these seasons corresponds to nearly 21 Earth years. But at the poles, there is only 1 summer and 1 winter, but they last twice as long as at the equator, 42 Earth years each. Because of this axial tilt, the polar regions of Uranus receive more energy from the Sun during the year than the equatorial regions. However, Uranus is warmer in the equatorial regions than in the polar regions. The mechanism at the origin of such a redistribution of energy remains unknown for the moment. Before the beginning of the research by the space probe Voyager 2, no measurement of the magnetic field of Uranus had been made. Before the space probe arrived on the orbit of Uranus in 1986, it was supposed that its magnetic field followed the direction of the solar wind. In this case, the geomagnetic poles should have coincided with the geographical poles, which are in the plane of the ecliptic. The data on the magnetosphere provided during the exploration of Uranus were particularly striking. This planet showed that it contains 4 magnetic poles at once, 2 main and 2 secondary. The structure of the magnetic fields of the different planets is generally similar. The lines come out of one magnetic pole, go around the planet at a certain distance, and enter it at the other magnetic pole. Thus, the planet is enclosed in a kind of magnetic cocoon. Its appearance is asymmetrical, since the solar wind, representing a flow of charged particles constantly coming from the sun and colliding with the magnetosphere, deforms it, squeezes it on the side facing the sun, draws it at a great distance on the opposite side, and thus forms the so-called tail of the magnetosphere. Near the Earth, for example, such an invisible trail extends over several thousand kilometers. The differences between the magnetospheres of the different planets are mainly related to the geometric dimensions, which are determined by the difference in the strength of the magnetic fields. But the magnetosphere of Uranus is completely unique, for two reasons. Not only its axis is very strongly deviated from the rotation axis of the planet by 60 degrees, but its center does not coincide with the center of the planet, but is distant from it by 1/3 of the radius of Uranus. Thus, the compass needle on Uranus will not point to the north, but to the magnetic pole, located at about 30 degrees latitude. On the Earth at this latitude are the Canary Islands, Delhi or Sydney. On the other hand, the strength of the magnetic field on Uranus varies considerably, changing from one region to another. In addition, there are also important magnetic anomalies on the planet, a kind of less powerful magnetic poles, which further complicates the picture of the structure of the magnetosphere. This strange alignment of the magnetic field of Uranus, combined with the very strong inclination of the rotation axis of the planet, results in a long corkscrew-shaped tail of the magnetosphere, which extends from the planet towards the outer edges of the solar system. The rotation of the planet, tilted sharply on the spin axis, twists the magnetic lines of force along the magnetospheric tail, like wires inside a string. The spacecraft measurements showed that the tail of Uranus's magnetosphere, stretched by the solar wind, extends at least 10 million kilometers or 6 million miles toward the orbit of the next planet in the solar system, Neptune. The magnetic field of Uranus is not only deviated at an abnormal angle from its rotation axis, but it does not even pass through the center of the gas planet. As a general rule, the magnetic field of a planet is generated by electrically conductive substances, which are transported by eddies near its core or directly inside. However, the magnetic field of Uranus is generated more near its surface, in the mantle. But even so, the reason why the field apparently forms only in a certain part of the mantle remains a mystery. The unusual magnetic field of Uranus operates independently of the axial plane of the planet and the position of its core. Scientists propose a theory which explains that the magnetic field of ice giants forms at relatively shallow depths. For example, the field would form in the ocean of liquid ammonia in a thin convective envelope surrounding a liquid core with a stable, layered structure. The moons of Uranus play an important role in the magnetosphere of the planet. In fact, these moons form large cavities in the magnetic field. The particle flux is high enough to darken the surface of the moons in about 100,000 years. This may be the reason for the dark coloration of the moons and particles in the rings of Uranus. The planet has well-developed aurorae, which are visible as bright arcs around the two polar poles. However, unlike Jupiter, on Uranus the auroras are not significant for the energy balance of the thermosphere. Uranus had already been observed in the night sky since the 1690s. Nevertheless, astronomers displayed it on their maps but considered it as a star. Uranus was the first planet discovered with an optical telescope. William Herschel, a 42-year-old professional musician, made his living teaching music and playing the violin and oboe in a local orchestra, but astronomy was his main passion. Between music lessons, he polished metal mirrors for telescopes, and after evening concerts, he spent his nights stargazing. On March 13, 1781, he studied the position of the stars in the region of the constellation Taurus. One of the stars in this area seemed strange to Herschel. Instead of a bright spot, it looked like a small disk. So he made the following entry in his observational journal: unusual appearance, either a star surrounded by a nebula or a comet. 2 months after Herschel's discovery, the parameters of the orbit of this celestial body were calculated. They showed that it revolved around the Sun in a circular orbit, characteristic of only planets. It became clear that Herschel had managed to discover a new planet, the 7th planet. Thus, the solar system, whose boundaries were still drawn along the orbit of Saturn, doubled overnight. The year of the discovery of the new planet, Herschel was elected a member of the Royal Society of London and obtained a doctorate from Oxford University. King George III, himself a great lover of astronomy, raised him to the rank of knight and appointed him in 1782 as Astronomer Royal. For a long time, almost nothing was known about Uranus except for its existence. Its real discovery took place only in 1986, when the interplanetary probe Voyager 2 visited the immediate vicinity of this mysterious planet. It became the first, and so far, the only spacecraft to make a huge tour of the outer part of the solar system, visiting the 4 giant planets. Launched from the spaceport of Cape Canaveral, Florida on August 20th, 1977, Voyager 2 reached Uranus almost 9 years later. To reach such a distance, the station had to use the help of the 2 largest planets of the solar system, Jupiter and Saturn, during its journey. Each of the 2 planets, with its powerful gravitational field, had a strong impact on the tiny station. As a result, its speed increased, and the flight path changed abruptly. The station performed 2 left-handed circumnavigations before reaching Uranus on January 24, 1986. Thanks to such gravitational maneuvers, Voyager 2 reached Uranus much faster than if it had traveled all the way, only by means of the force impulse received from the Earth. Its trip would have then taken about 30 years. By passing close to Uranus, Voyager 2 collected new information about this distant planet. Most of the information known today about Uranus was obtained in a few hours, while the station was close to the planet, moving at a distance of 81,500 kilometers, or 50,000 miles, from the surface of the clouds, at a speed of about 46,000 kilometers per hour, or about 28,500 miles per hour. Cameras mounted on a rotating platform were continuously filming the planet and its moons, rotating automatically, according to a predetermined program. During the flyby, by Voyager 2, the axis of rotation of Uranus, which is almost in the plane of its orbit, was directed towards the Sun, so that the photographs obtained show only the southern hemisphere of the planet, which was illuminated at that time. In the photographs, 10 small moons previously unknown were found at the same time, and 5 large moons are photographed in detail. The station also discovered the magnetic field of Uranus and studied the structure of its magnetosphere. It turned out that the magnetic field of this planet was quite unique. The magnetic lines of force it contains are not stretched in a straight line, like those of other planets, but are twisted into a double helix. In 2011, a group of 168 scientists submitted a proposal to the European Space Agency describing a journey to the outer solar system, to the planet Uranus as the final destination. The mission is called Uranus Pathfinder. It will study the unique chemical composition of the planet, its rings and moons, as well as reveal some of the planet's most important secrets. This mission, in turn, will increase our knowledge of the solar system. The project leader said that the goal of this mission is to explore the outer solar system, about which we know very little. Depending on the size of the spacecraft, the mission could take 8 to 15 years to reach its final destination, Uranus. Although several Uranus space missions have been developed, none has yet been planned. Today, we continue to collect information on the ice giant thanks to observations from the Hubble Space Telescope and from several powerful ground-based telescopes. Like the other planets in the solar system, Uranus probably formed about 4.5 billion years ago in an ancient massive cloud of gas, dust, and ice that collapsed into a spinning disk. The material that contributed to the formation of Uranus and the other giant planets was sufficient to allow the planets to become so massive. Scientists believe that the differences between the ice giants and the gas planets, i.e. Saturn and Jupiter, are due to their slightly different formation histories. Unlike most gas giants, Uranus has a rocky rather than a gas core. The core probably formed first, then gathered the hydrogen, helium, and methane that make up the planet's atmosphere. The heat of the core determines the temperature and weather of Uranus, dominating the heat from the distant Sun, which is nearly 3 billion kilometers or 1.8 billion miles away. Another model, called the NICE model, proposes that Uranus and the other giant planets formed in much more compact orbits than they are today. A large disk of rock and ice surrounded them, extending about 35 times the Earth-to-Sun distance, just beyond the current orbit of Neptune. As the planets interacted with the smaller bodies, they scattered most of them toward the Sun. The process caused them to exchange energy with the objects, sending Saturn, Neptune, and Uranus in the opposite direction of these smaller objects, i.e., farther out in the solar system. Finally, the small objects took the direction of the internal solar system until reaching Jupiter. Jupiter, because of its mass, sent most of these small objects flying to the edge of the solar system, or completely out of it, forming the Oort cloud. The motion between Jupiter and Saturn drove Uranus and Neptune into even more eccentric orbits, sending the two ice giants through the remaining ice asteroid disk. Some of the material was thrown inward, where it crashed into the terrestrial planets in the late bombardment. Other material was thrown outward, creating the Kuiper Belt. As they slowly moved outward, Neptune and Uranus swapped places. Eventually, interactions with the remaining debris caused the two ice giants to settle into current orbits. Along the way, it is possible that one or even two other giant planets were expelled from our solar system, leaving doubt about a possible ninth planet. The planet has a particular structure that differs from other gas giants. Of course, further studies are necessary, but on the basis of the available data, scientists have managed to build a model of the structure of Uranus. Despite the fact that the radius of Uranus is slightly larger than the radius of Neptune, its mass is a bit lower. This data supports the hypothesis that Uranus is composed mainly of ice, ammonia, and methane. Hydrogen and helium represent only a small part of the total mass. The remaining fraction is made of rock, which would correspond to the core of the planet. The internal structure of Uranus can only be considered through indirect evidence. Since the density of Uranus is low, it is thought that at the very center of Uranus is a rocky core, composed mainly of silicate, iron, and nickel. The core occupies only 20% of the planet's radius, a diameter which corresponds to 1.5 times the size of our whole Earth. Around the core is a liquid mantle, which occupies 60% of the planet's radius. It is composed of a mixture of water, ice, and rock. But this ice is not at all like we imagine. The mantle is heated to 5,000 degrees Celsius, or 9,000 degrees Fahrenheit, and it is under enormous pressure. This mixture of water, methane, and ammonia is in a special state called superionic hot ice. The ice shell is not actually ice in the conventional sense of the word, as it is made up of a hot, dense liquid that is a mixture of water, ammonia, and methane. This highly electrically conductive liquid is sometimes called the aquatic ammonia ocean. Even higher up is the global ocean of liquid hydrogen, and then a very intense atmosphere that occupies another 20% of the planet's radius. Other models suppose that Uranus would not have a solid core at all. In this case, Uranus would look like a huge boiled snowball, made of a mixture of liquid and ice, surrounded by a gaseous envelope. The composition of Uranus is very different from that of Jupiter and Saturn because of the presence of ice, which dominates over gas. No wonder that Uranus is also called the ice giant. The planet Uranus does not have a solid surface. In fact, the gas of the atmosphere is transformed into liquid layers at the depths. It is impossible to specify exactly where the boundary of this surface exists. Therefore, the surface is considered to be the point where the pressure is 1 bar, and everything above this value is considered to be the atmosphere. We will not be able to walk on the surface of Uranus or land a spacecraft on it. We will simply drown. When Voyager 2 arrived around Uranus, one of its main objectives was to study the atmosphere of the planet. The spacecraft identified the size of Uranus. In fact, the diameter of the planet, depending on the level of the cloud layer, turned out to be about 51,000 kilometers or 32,000 miles, which is about 4 times larger than that of the Earth. The upper limit of Uranus's atmosphere, which is about 7,000 kilometers or 4,000 miles thick, is made of clouds. The atmosphere contains 84% molecular hydrogen, 14% helium, 2% methane, and small amounts of acetylene, hydrogen cyanide, and carbon monoxide. The outer part of the atmosphere is very transparent. The greenish-blue color of the gaseous envelope of Uranus is the result of the absorption of red rays by the methane present in the atmosphere. Although Uranus does not have a solid surface In the usual sense of the word, the farthest part of the gaseous envelope is generally called the atmosphere. It is thought that the atmosphere of Uranus starts at a distance of about 300 kilometers from the outer layer at a pressure of 100 bars. The atmospheric corona extends to a distance of 2 times the radius of the surface with a pressure of 1 bar. The atmosphere of Uranus can be divided into 3 parts. The troposphere occupies an altitude range from 300 kilometers to 50 kilometers, where 0 kilometers is taken as a conditional limit, where the pressure is 1 bar. That is, the troposphere occupies an altitude range from 186 miles to 31 miles, where 0 miles is taken as the conditional limit, where the pressure is 1 bar. In this area, the pressure is between 100 bar and 0.1 bar. This part is responsible for most of the infrared radiation of the planet and allows to determine the effective temperature of Uranus. The stratosphere covers heights from 50 kilometers to 4,000 kilometers, that is from 31 miles to 2,500 miles, and pressures between 0.1 bar and 10 to the minus 10 power bar. In this part, the temperature does not decrease, but on the contrary, it increases with altitude. This heating is due to the absorption of infrared and ultraviolet solar radiation by methane and other hydrocarbons formed due to the photolysis of methane. The thermosphere, or atmospheric corona, at a height of 4,000 to 50,000 kilometers from the surface, that is a height of 2,500 miles to 31,000 miles, the pressure in this layer tends towards 0, with great distance from the center of the planet. It is here that the temperature is the highest. The thermosphere of Uranus and the upper stratosphere form the ionosphere, which is located at altitudes between 2,000 and 10,000 kilometers, i.e. between 1,200 miles and 6,200 miles. The ionosphere of Uranus is denser than that of Saturn and Neptune, perhaps because of the low concentration of hydrocarbons in the upper stratosphere. The ionosphere is maintained mainly by solar ultraviolet radiation, and its density depends on the solar activity. Using various filters, Voyager 2 photographed atmospheric haze belts over the planet's south pole, which at the time of observation was located in the center of the sunlit hemisphere. This haze was formed when the sun's ultraviolet rays passed through the atmosphere of Uranus. In some places of the upper atmosphere, white cloud formations are visible, probably made of methane frost. It seems that due to the extremely uneven distribution of solar heat on Uranus, there should be a colossal difference in temperature between the light and dark regions of the planet. One would expect the pole, which has been facing the sun for so long, to become significantly warmer than the dark one, but it seems that nothing of this kind is happening. The temperature measurements of the upper atmosphere of Uranus were taken from the Voyager 2 station just as winter and summer at the poles were reaching their maximum evolution. It turned out that the temperature values at the 2 poles and at the equator are almost the same. This indicates the presence of a heat transfer mechanism in the atmosphere of Uranus, from the warmest to the coldest regions, and vice versa. The hypotheses about the circulation of the atmosphere of Uranus have not been confirmed either. All the calculations concerning the dynamics of the air envelope of the planet were based on the fact that when one of the poles of Uranus is facing the sun, it is continuously illuminated, whatever the rotation of the planet around its axis. Therefore, one would expect that in the pole region, long warmed by the sun, the warm air would rise and move towards the equator, and then further towards the unlit side of the planet, where it would start to cool down, become heavier, and sink into the depths of the atmosphere in the shaded pole region. The general pattern of atmospheric circulation on Uranus is dominated by transfer in the direction of the planet's rotation. Thus, the cloud bands here are tapered from west to east, as shown in the probe images. However, it was quite difficult to determine this, because in the atmosphere, it was possible to notice only very few individual cloud formations, whose color differs from the general homogeneous cloud mass that envelops the whole planet. These white clouds are most probably made of methane, which are located at an altitude where the temperature is about minus 200 degrees Celsius or minus 328 degrees Fahrenheit. Uranus, like the three other gas giants, Jupiter, Saturn, and Neptune, is located in the outer part of the solar system, extremely far from the Sun. Therefore, even on the day side of this planet, the temperature is very low and very homogeneous on the whole planet. Measurements taken at the upper limit of the atmosphere of Uranus, on the side of the illuminated hemisphere, is almost identical to other measurements taken in different regions, from the pole to the equator. The difference is only 4 degrees Celsius. Thus, the temperatures measured during the passage of the probe fluctuated between minus 208 degrees Celsius and minus 212 degrees Celsius. That is to say, between minus 342 degrees Fahrenheit and minus 346 degrees Fahrenheit. This phenomenon was one of the surprises that Voyager 2 presented to scientists during the exploration of Uranus. Like other giant planets, the atmosphere of Uranus shows signs of strong winds blowing parallel to the equator of the planet. These winds are blowing from west to east, with hurricane speeds between 140 and 580 kilometers per hour. That is between 90 and 360 miles per hour. But strangely, along the equator, the winds blow in the opposite direction, with speeds higher than 350 kilometers per hour, or 217 miles per hour. The planet Uranus is not the farthest from the Sun. After all, there is Neptune. However, it is the coldest planet. At a certain moment, the temperature of the atmosphere reaches minus 224 degrees Celsius. That is minus 371 degrees Fahrenheit. Such coldness is observed both on the illuminated side and on the night side. It is not known why the ice giant is so cold. Some scientists think that the reason is the tilt of its rotation axis. Others suggest that as a result of the probable collision with another celestial body, Uranus has lost most of its internal heat, and the temperature of the planet's core has decreased. We know that the other giants emit more heat than they receive from the Sun. Even Neptune, which has similar characteristics to Uranus but is much further away, emits 2.6 times more heat than it receives. The energy is released due to gravitational contraction and core rotation. But Uranus emits even less heat per square meter than the Earth, i.e., it emits almost no heat at all. This very strange characteristic has not yet been clearly answered. Some assume that the heat released from the depths of the planet simply cannot escape from the atmosphere. This barrier could be a layer of the atmosphere with a different composition. The absence of excessive thermal radiation from the planet makes it much more difficult to determine the temperature of its core. However, if we assume that the temperature conditions inside Uranus are close to those of other giant planets, then the existence of liquid water is possible in the depths of this giant, and therefore, Uranus can theoretically Be among the planets of the solar system where the existence of life is possible. On March 10, 1977, while one of the stars was covered by Uranus during observations aiming at studying the atmosphere of the planet, astronomers recorded a 1-minute decrease of the luminosity, then 4 other eclipses at a lesser distance from the planet during several seconds. After the eclipse of the planet, the observed star again experienced the same 5 strange eclipses. This is how the rings of Uranus were discovered. In total, 9 rings were discovered. Today, the number of rings discovered is 13, the outer ring being located at more than 72,000 kilometers or 45,000 miles from the planet. Saturn's rings are beautiful, but many people simply don't know that other giant planets are similarly decorated: Jupiter, Uranus, and Neptune. Of course, the rings of Uranus are not so impressive, but they are real. Unlike the bright rings of Saturn, those of Uranus are very dark. Bond's albedo for the particles that penetrate it does not exceed 2%. The chemical composition of the ring particles is unknown. However, they cannot be made of pure water ice like Saturn's rings, for example, because they are too dark, even darker than the inner moons of Uranus. This indicates that they are composed of a mixture of ice and dark matter. The nature of this substance is unknown, but it may be organic, considerably darkened by the irradiation with charged particles from the magnetosphere of Uranus. It is possible that the rings are composed of highly transformed matter, initially similar to that of which the inner moons of Uranus are composed. From Earth, they can only be detected in large observatories, and not always, because they are thin and reflect light weakly, unlike the bright rings of Saturn. They consist of small dark particles, ranging in size from a few micrometers to several meters. The rings were named by the first letters of the Greek alphabet, in order of distance from the planet: Alpha, Beta, Gamma, Delta, Epsilon, etc. Currently, 13 rings have been found around Uranus, which differ not only in color and brightness, but also have large gaps. Scientists think that they were formed recently. Their age does not exceed 600 million years. The origin of the rings is probably one of the moons of Uranus, which collapsed either during a collision with a celestial body or under the influence of the tidal forces of the gas giant. The moon is fragmented into smaller and smaller particles, forming now the 13 rings of Uranus. The Epsilon ring is located at 52,000 kilometers, or 32,300 miles from the center of Uranus, and is the brightest. Either its albedo is the lowest among the other rings, or its constituent blocks are closer together. The rings of Uranus are made up of many small, separate bodies of a maximum size of 4 to 6 meters, or 20 feet at most, as none of them completely block the sunlight, but only weaken it, and to varying degrees in different parts of the rings. Unlike the bright rings of Saturn, the rings of Uranus are very dark. They reflect only 2% of the light falling on them, which means they are blacker than coal. Uranus is surrounded by a system of moons, most of which almost coincide with the plane of the planet's equator. Thus, the moons of Uranus do not move in the plane of its orbit, as is the case with the moons of all other planets, but almost perpendicular to it. This is a unique case in the solar system. Today, 27 moons of Uranus are known. Interestingly, the discoverers of the first 4 moons did not give them names. This was done in the 19th century by the son of William Herschel. Contrary to astronomical tradition, which requires that planets and moons be named after gods and creatures from Greek and Roman mythology, the moons were named after characters from the works of English writers such as Shakespeare and Alexander Pope. The brightest moon of Uranus is Ariel, reflecting 40% of the light that falls on it. Therefore, it was named after the kind and brilliant spirit of the character found in both Shakespeare's play The Tempest and Pope's poem, The Rape of the Lock. The neighboring moon, Umbriel, is almost the same size, but its surface is twice as dark, as it reflects only 20% of the light. It is named after the evil and dark spirit of the same poem by Pope. Even the moons that were discovered relatively recently in the 1980s were named after the heroines of Shakespeare's plays. The general picture of the lunar system of Uranus is the following. Between the rings and the main satellites, there is an inner group of 13 small moons, then 5 main moons that follow, and even further away, an outer group of 9 small moons. All the small moons are quite dark. They reflect only 7% of the light that falls on them. The 18 moons closest to the planet, including the 5 large ones, move inside the magnetosphere of Uranus, without ever leaving it. This makes the picture of the structure of the magnetosphere even more complex, because the moons have a certain influence on it. None of the moons of Uranus has an atmosphere. They are all too small to contain a gaseous envelope around them. The 5 large moons are composed of 50% water ice, 30% methane and ammonia ice, and 20% ordinary rocks, such as silicates. The composition of the others remains unknown, but there is a theory that they were formed from asteroids captured by the gravity of the planet. Comparing the moons of Uranus to those of the other giant planets, the first ones are distinguished by a small mass. Even the total mass of the 5 largest moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, does not reach half the mass of Triton, the largest moon of Neptune. To better understand their size, imagine that the surface of one of these moons is smaller than the area of the Australian continent. The largest moon of the ice giant, Titania, is the 8th largest moon in the solar system, and is distinguished by huge systems of fissures up to 5 kilometers deep, canyons and craters up to 326 kilometers or 200 miles in diameter, which indicate a period of active geological activity in the past of this moon. These details may be the result of tectonic movements of the crust. Its diameter is 1,578 kilometers, about half the diameter of Earth's moon. Like our moon, Titania always faces one side of Uranus. The second largest moon, Oberon, is the furthest from Uranus. Its evolution is practically not influenced by the magnetosphere of the mother planet. Moreover, Oberon has been recognized as the reddest moon of the Uranus system because of the presence of a large amount of dark red matter of unknown origin on its surface. Half ice and half rock, Ariel is one of the smallest globular moons of the solar system. Its surface has a complex topography, which consists of deep canyons, cliffs, and valleys, with signs of geological activity. It is thought that only the strong influence of the tides of Uranus, which stretches the entrails of its icy moons, saves it from a complete geological death, which occurs because of the rather close location of this moon with respect to its neighbor. Let's go meet its neighbor, Umbriel. Ariel's neighbor Umbriel is officially recognized as the darkest moon of Uranus because of its extremely low reflectivity, which is only 16%. Umbriel is thought to be one of the most cratered moons in the satellite system, with craters, particularly large on this moon, reaching 200 kilometers in diameter. The dark shades of Umbriel's surface may be the result of a layer of dust and small solids that once lay close to the orbit of this moon. Finally, Miranda is one of the strangest bodies observed in the solar system. It is known as the ugliest moon in the solar system. The images of Voyager 2 showed parts of the surface of the moon with a resolution of 1 kilometer. In these images, you can see that the surface layers are made up of huge fractured canyons up to 20 kilometers deep, terraced layers, and a mixture of old and young sections. Scientists explain this by the fact that this small moon of Uranus suffered at one time a catastrophe that caused its complete destruction. Sometime later, Miranda managed to reconstitute itself in an incomprehensible way, which is why the surface of the satellite is today an icy desert dotted with shapeless protuberances. The unusual tilt of Uranus's rotation axis is one of its most impressive features, but astronomers still do not know exactly why the object ended up in this position. Most of the planets in the solar system have their poles more or less oriented in the same direction, and most of them turn counterclockwise when seen from above. The orientation of Uranus in space differs from the rest of the planets. At the time of the birth of our solar system from a rotating disk of gas and dust 4.5 billion years ago, all the major planets were placed in orbit near its flattened plane, which represents the ecliptic. This was the inevitable result of the laws of large numbers and the conservation of momentum. Since the planets were formed as a result of the collision of innumerable particles, any random motion had to balance out so that the planets would continue to rotate in a strictly vertical position relative to their orbits. However, it is obvious that this is not the case. If Mercury and Jupiter are indeed more or less vertical, then the Earth, Mars, Saturn, and Neptune are tilted at an angle of about 25 degrees, and Uranus even more so, with an angle of 98 degrees. This means that the axis of rotation of Uranus is almost in the plane of its orbit. In fact, the motion of Uranus around the Sun is quite special. It drags along its orbit, turning from one side to the other. Such characteristics of the motion and rotation of Uranus do not fit with the general picture of the emergence of a planet from a pre-planetary cloud, whose parts were rotating in the same direction around the Sun. But what has turned many of the large planets in the solar system from their axes? For telluric planets like Venus, the answer is probably interplanetary collisions. Collisions with a larger planet could easily throw them into oblique trajectories or change the momentum of the planet. However, giants are by definition large, so it takes a lot of force to cause a large tilt. For a collision to deviate the axis of Uranus by 98 degrees, it would require a collision with a planet the size of the Earth. But mathematical models do not indicate the possibility of the existence of a celestial object of this size in the outer part of the solar system. Today, there are two theories explaining this tilt. According to the first dominant theory, the tilt was caused by the collision of Uranus with a small planet the size of the Earth at the beginning of its formation, and since the moons of the planet do not have such large tilts, the collision occurred shortly after the formation of our system, when Uranus was surrounded only by a disk of gas and dust, from which satellites were formed later. As a result of this collision, the rotation axis of Uranus has strongly deviated from its original direction and has remained in this abnormal position. According to the second theory, the tilt was caused by a massive moon of Uranus which disturbed its orbit for millions of years. Afterwards, this moon was either expelled from the attraction of Uranus or collapsed by the tidal forces of the gas giant, forming some small moons still present today around Uranus. Nevertheless, there are several important inconsistencies in these hypotheses. For example, they cannot explain why none of the moons of Uranus has the same inclined orbit. Moreover, these moons are icy, and a powerful impact sufficient to reverse the rotation axis of the planet would have generated a large amount of heat that would have vaporized the ice of these moons, making them rocky. The planet is surrounded by a set of moons and rings. A collision of a celestial object with a parent planet should have dispersed all these small bodies in space. The formation of this set of moons and rings due to this collision is to be excluded because the differences in the chemical composition of the moons and the gas giant suggest that they most probably came into existence well after the formation of Uranus. On the other hand, two astronomers from the University of Maryland have proposed a new scenario that resolves these contradictions. According to their hypothesis, Uranus could be tilted laterally by a system of giant rings. Today, the rings of Uranus are very thin and are made of smaller dust particles. But scientists think that at one time these rings could have been much more massive. The fact that the rings have a relatively short lifespan on the scale of the cosmos is highlighted by data obtained by the interplanetary station Cassini, which studied the rings of Saturn. The model of the two astronomers suggests that a large ring system has swung Uranus around its axis with a noticeable precession of rotation, a bit like spinning a top that starts to wobble. Then, if the precession of the planet's rotation axis entered in resonance with the orbital precision of the planet could have turned around. The resonance between spin and orbital precession is known as spin-orbit resonance, which can generate a large axial tilt. This type of resonance is thought to have caused Saturn's axial tilt relative to its closest cousin, Jupiter. Previously, to explain the axial tilt of Uranus, the spin-orbit resonance hypothesis had already been put forward, but the hypothetical planet X was proposed as the body that caused the resonance. The two researchers believe that the ring system, which is part of the formation of giant planets, is better suited to this explanation. They modeled Uranus and Neptune with large disks to see how they interact with the planets, and found that the ring system can tilt the planet's rotation axis by 70 degrees over a period of 1 million years. This model easily explains the axial tilt of 30 degrees of Neptune, but for Uranus it does not allow to conclude. There was an additional impact, and the theory of a collision with another celestial body is still discussed. But in this context, it could be small asteroids rather than large celestial objects, which makes this scenario more likely. The authors add that a subsequent collision with an object that is about half the mass of the Earth could have tilted Uranus between 70 and 98 degrees. Thus, it is quite likely that impactors with relatively small masses, about the size of our moon, but of a certain number, could increase the probability of creating spin states of Uranus. Each of these theories has its advantages and disadvantages, but for the moment, the enigma of Uranus's inclination is not yet solved. Another particularity of Uranus is its smell. The clouds in the upper atmosphere of Uranus are mainly composed of hydrogen sulfide, the gas which is mainly responsible for the stench of rotten eggs or human flatulence. To discover this surprising characteristic, let's examine the chemistry of Uranus. A team from Oxford University turned to the Gemini Observatory, a pair of infrared telescopes atop Mauna Kea Mountain in Hawaii. The investigators hoped to analyze spectral lines, essentially the chemical fingerprints of gases in Uranus's atmosphere. Infrared and near-infrared observatories have been in operation for a long time, but the distance to Uranus has made it nearly impossible to use these systems to get a clear picture of the planet's chemistry. To solve the mystery, researchers observed the sunlight as it passed through a backlit Uranus. This very particular moment allowed them to measure a multitude of other variables, notably the atmospheric temperature, pressure, humidity, saturated gases, and, notably, the presence of hydrogen sulfide. So, if you could go through the clouds of Uranus and take off your helmet, you might be surprised by a rather unpleasant smell. Another characteristic of the ice giant is its color. This blue-green color of Uranus is due to its atmosphere, which is mainly composed of hydrogen and helium, as well as smaller quantities of methane. It is this methane that gives the planet its color, because methane reflects blue light. When sunlight, consisting of all the colors of the spectrum, hits the planet, the methane absorbs some of the redder colors, and the blue wavelengths are reflected. This makes the planet blue. Uranus has a peculiar appearance. Not only is its blue color striking, but it is also pale, giving the impression that the planet glows softly. Researchers suggest that it is the large amount of hydrogen sulfide, ice, and photochemicals in the planetary atmospheres that has led to this hazy appearance. There are layers in the atmosphere, and as these materials move upward, they become more concentrated until the methane condenses. This condensed methane makes the atmosphere hazy. The atmosphere of Uranus is very thick, so the methane in the atmosphere reflects more blue light, which gives it this blue-green hue. The atmosphere of Uranus is unusually quiet compared to the atmospheres of other giant planets, even compared to Neptune, which is similar to Uranus in composition and size. When Voyager 2 approached Uranus, it was possible to capture only 10 cloud bands in the visible part of this planet. Such a quiet atmosphere can be explained by an extremely low internal heat. It is much weaker than that of the other giant planets. Therefore, Uranus seemed to be a dynamically dead planet. Several years later, observations from the Hubble telescope have shown that the seasons on Uranus have changed since the Voyager 2 flyby. This change of season has affected the weather conditions of the planet. Although the climate on Uranus is calmer, dark spots were observed in 2006, and for the first time a vortex was seen and photographed in its atmosphere. This phenomenon shows that there can be powerful storms on Uranus, due to the fact that the surface of the planet, which has not warmed for 42 years, starts to warm up at the change of season. It is worth noting that such storms occurred 7 years after Uranus's approach to the Sun. In addition to the storms on Uranus, astronomers have detected diamond showers falling thousands of kilometers below the surface of Uranus. Astronomers note that carbon and hydrogen are compressed due to the extreme temperature and pressure in the atmospheres of this planet. Thus, diamonds form, fall and settle around the solid core of Uranus. In fact, astronomers have proven that on planets like Uranus and Neptune, there is a high methane content in the atmosphere. This means that during the decay of methane, carbon and hydrogen are released, which then, under the influence of high pressure, penetrate the lower layers of the atmosphere. The methane is then able to fall directly to the center of the planet and turn into diamonds. This is quite a theory that has become reality thanks to an experiment carried out by scientists from the University of California. In this experiment, styrene, which is a chemical element similar to methane, was used to fill the experimental atmosphere. The atmosphere itself was compressed to a pressure of over 1,000 bars, which is a gigantic pressure comparable to the most powerful press in the world, and heated to 5,000 degrees Celsius, or 9,000 degrees Fahrenheit. At the end of the experiment, the resulting carbon began to transform into diamonds. We now know that Uranus is very different from the other planets of the solar system. It is a special world with its own characteristics and mysteries. The last time a spacecraft approached Uranus was in 1986. It was Voyager 2 that allowed astronomers to take a closer look at the huge ice giant with an atmosphere of hydrogen, helium, and methane, which has many moons and a strong magnetic field. But until now, scientists know too little about the seventh planet of the solar system. Studying Uranus could explain why such planets are often found in the Milky Way, and shed light on what secrets this ice giant, Neptune's neighbor, is hiding from us. The U.S. National Academy of Sciences has tasked NASA with sending a spacecraft to Uranus as soon as possible to find out more, and has been considering options for exploring the planet. With any luck, a mission to Uranus will be launched by 2034. According to the preliminary plan, the spacecraft will orbit Uranus and occasionally fly near its moons. This spacecraft will send a small probe into the atmosphere of Uranus for further study of the planet. This will help to explain many unexplainable facts. According to scientists, with the help of a new space mission, it will be possible to answer several important questions and unravel the mysteries of Uranus. Why are such ice giants so common in the Milky Way? Why is Uranus the coldest planet in the solar system? Why is the axis of Uranus tilted in such a way that it almost coincides with the plane of its orbit around the Sun, and that its poles are located where the other planets have an equator? But if NASA can meet the 2034 deadline, the mission will take 12 years to reach its destination. Therefore, such a mission will be designed for the next generation of scientists. The study of Uranus can provide more information, not only about the formation of the solar system, but also about our galaxy in general. Uranus is undoubtedly the most unusual planet in the solar system. There is still a lot to learn to help us better understand the many mysteries around this icy world.